Hello, and a big welcome back to all my subscribers. And if you're not a subscriber, what's wrong with you? Right. Today I'm going to carry on with the RISC-V assembly. We're going to look in detail, and I've written a simple program that basically counts to 10, but it does show all the parts of a typical assembly program. This includes instructions, labels, directives, macros, the registers, literals and immediate values, read-only values, data definitions, external references and symbols, and all of that. But before we get into that, let's first start by looking at the directory structure of the program that we're going to build. So if I show you the directory structure, you can see that what we have here is the there's a make file, there's the build directory, and the source directory. Now you can see the subdirectories build and source, but the make file is in the top level directory. So if we look at the make file, the make file is a script used by make, and the command is used to automate the compilation and linking of programs, particularly in assembly language programs, and it defines how to compile the source code into object files and then link these object files to create an executable. The make file uses variables, rules, and targets to organize and simplify the build process. So let's break this all down for a bit more clarity. So variables, for example, CC and AS, these are variables. So CC shows that it is equal to the GCC command, and AS is equal to the AS command. So the compiler is GCC, used for compiling and linking, while the assembler is for specifically assembling language programs. And then we have C flags and AS flags. These are options passed to the compiler and the assembler. So the -O0 disables optimizations to make debugging a bit easier. The M architecture is equal to RISC-V 64 IMFD blah blah blah, which specifies the target architecture for the compilation, which in this case is a 64-bit RISC processor, and the G adds debugging information to the output. And then we have the SR and build directories. These are variables that specify the location of where the source files are compiled, or where the source files are located in SRC, and the place to build the object files is in build. Now next we have targets and rules. So the target is all. So this is the default target that make will attempt to build if no specific target is specified. It, as in all, depends on the target. So this is the target, and this is the dependency, right? So this $brackets target, this target creates the final executable from the object files, and it uses the compiler variable with flags, the C flags, to link all of the objects. Now, the $caret in a make file is used to link all the object files, and the output is loop. So the target here translates to loop. So this is basically the shortcut for this command. So because in this example we're looking at $brackets target, this evaluates to $brackets target, but if you see down here, this will evaluate to the .o files, because the .o here, this is the target, and so this translates as the target output here, and then this is the list of files. So this is just input the list of files that it's going to use. Now, you'll notice here we also have clean. Now, clean is what is for cleaning up the project. So it removes all the generated files. It finds and deletes any files, temporary files created by editors, removes the target executable and the object files. So this is what is known as a phony thing, a phony build. You're not actually building anything, but you're using make to run this. So now let me just go through these special symbols again. So the $@ sign, the $, and the $less than are automatic variables in make, and the $@ symbol refers to the name of the target being generated. And then the $, refers to all the prerequisites or dependencies of that target. And then the $less than symbol here refers to the first prerequisite of the rule. Now, these have lots of other pattern substitutions. For example, we have wildcard pattern substitution. So in this example, it's substituting the S, so the name of the file, whatever it is, Fred, Bob, but it doesn't matter, .s, and converts it to Fred, Bob, .o. So it's basically just pattern matching, pattern substitution. So a regular expression, really. So when you run make in the directory containing the make file, what it does is it looks for the first target in the make file, which is all, and the all target depends on the $target, which is in loop. And to build loop, make needs to build the object files, which are derived from the source files in SRC. So each .src file is assembled into a .o file using the rule for $build directory. And then after all the .o files are created, they are then linked into the final executable of loop. So now you can see we have a loop here in our directory. Now if we run make clean, if we run make, then nothing will happen because make knows that it has already built everything. And then we can run the dummy make clean, and it removes everything. Again, you can see that the loop is gone. And then we can just run make again, and it knows that it now needs to rebuild everything because it has removed, when I did make clean, all of the other stuff. So make automates the process of building of programs, and it creates an efficient and error-free way to do it, especially as projects grow in complexity and difficulty. So let me just run the program for you, and you can see it's amazing. It counts to 10. So it's nothing particularly wonderful. But if we look at the loop.s program in the source file, this is the program that I've written. So this code is a simple assembly program that just counts from 1 to 10 and prints each number using the printf function from the C standard library. So it's a basic example designed to introduce several key concepts of assembly programming. Now let's break down the different parts of the program and how they work together. So one of the first things you'll notice is we have a lot of instructions. Now instructions like li is load immediate. So this instruction loads an immediate value into a register. For example, this loads the number 1 into the register S2. Okay. Now the reason that we're using S2 is because this is a saved register. It won't get clobbered by functions and print functions and things. And then we have LA. Now LA loads address. So here we're loading an immediate value of 1. Here we're loading an address. And if in terms of C, we're loading a pointer basically into the register. So this loads the address of the variable or label into the register. And here we're loading increment. And increment is defined up here. And then we have load word. So this loads the value at the address. So here we load increment, the address of increment, into the temporary register T0, and then we load the value which is located in T0 at that memory address into S3. So this is load word. So it reads a word-sized value from the memory into the register. And it loads it starting at the address in T0 at 0, right? So starting at 0 of memory location T0, and it loads that word. And then we have other instructions here like add. So add adds 2 registers values and stores the result. Adds 2 values and stores the result in the register. Now in this example, because we just want to increment what is currently stored in S2 by 1, this adds 1 to S2 and stores the result in S2. Okay? And then we have branch if less than, so BLT, not the sandwich. And it compares the 2 values in the registers, and if S2 is less than S3, then it jumps back to loop. Now, what is loop? Loop is a label, and labels are markers at a point to locate certain locations in code, and they're used to identify sections of the program easily. So the beginning of a loop, or to mark data. So up here, message is a label that marks the data for message. Increment marks the label for this value. And then we have directives. So now directives are not actually for the CPU. They are not for execution. These are actually instructions to the assembler. Okay, so when it starts to do things. Now this is a directive. So we're saying section dot data. So here we're declaring this, everything that follows here is data. And so we define the label message. We say that it is an ASCII string with null terminated. So the Z is a null terminated string. So we don't have to add a 0 at the end. It does it automatically. And then we move on to the next section. So here we're declaring that this is code. And realistically, this should be up here. But the assembler doesn't really care because it can work out what's happening. But for us humans, it would be better if we move to the section for data here, and we define that. And then we have a section for read-only data. Now, .ro data is read-only data. So what we're saying here is this increment, we don't actually increment this value. This is the value we're incrementing toward. And we've defined it here as a word and in hexadecimal. So you can define these as binary, in hexadecimal, or in decimal, right? So we're saying we want 11, right? Which is B in hexadecimal. And then the next section is text. Now, weirdly, it's just a historical thing. .text means code. So you're declaring the code here. And the next directive is global. Now, this makes a symbol or a label accessible to the linker. So what we're saying here is that here we're telling the assembler, when you create the object files, make sure that you are inform the linker that main is a global function and it's visible to the linker. So having done this, so .text contains executables, .data is used for declaring or initializing data, and .ro holds read-only data like constants. So if you're used to C programming, then this would be a const or a define, you know, and you would put them in this bit here. So you'll notice that there are comments here at the end of pretty much every line. Now in GNU assembly, you use the pound mark, this hash here, to denote a comment. Some assemblers use this, but the GCC, the GNU one, does not use that. So remember that it uses the pound or the hash, so make sure to use hash for your comments. You will get a compiler error if you don't. But comments are used to explain your code. Now the program doesn't include comments, but adding them helps explain the purpose of each instruction in each section. And as your programs get bigger, you will want to know when you go back, what is this thing doing? What is this section doing? Without having to try and read all of the code, because it's not as easy to read as a higher level language like C or Java or whatever. So it's always good to have lots of comments in here when you're doing an assembly language program. Now, the next thing we have here is a macro. So a macro allows you to reuse code blocks through a single instruction. Now, this macro, where dot macro is the definition, the name of the macro, and then any arguments that are passed. And then if the argument is passed, where it's used, you put a backslash. Now, all we're doing here is we're moving the message. So we're doing LA, so we're loading the address of the message into A1. And if you saw the last video, you'll remember that I said when you call, the system will expect certain things to be in certain registers. So when you call printf, the library function, it expects that the message is in the first argument, the A0, and that any subsequent things, like here we have the message, but we want to substitute the digit or the decimal here. So that is the subsequent argument. That needs to go into the next register, A1. Now, because this is a macro, this would just get substituted for whatever we put when we call the macro. And then this calls the system function, and then this is the end of the macro. So down here we use the macro. We just call print number, and then we give it the register where the value is located. Now, registers are small storage locations within the CPU. Now this program uses lots of different registers. We're using S2, S3, A1, A0, A7, T0, and in a RISC processor, the actual name of all of the registers is simply X, and it goes X0, X1, X2, X3, X4, X5, but they are aliased to various usage. So you will find an SP for stack pointer. You will find T0 for a temporary register. S0, 2, 3, these are for saved registers. These are registers that won't get clobbered when you make a system call like this one. So if you need to keep it after a system call or during a system call, you need to put it in one of the S registers. Now, you can just use the X name. So, for example, you can compare to, for example, 0. That is because the register X0 is equal to 0, always. It doesn't matter what you try and move or in or out of this register. This register is fixed in hardware to the value of 0, which means you can always use it to compare to 0. So if you need to compare here, if it was greater than 0, you could just use X0, that register, to compare it against, or the alias 0. Now, we'll use some of this later, but it's just good to know. And you should, if you can, get the book by Robert Winkler to look at RISC programming. Have a look at that, and he does address all of the registers. And this information is available online, so it's nothing special. Now, we also have here external references. And PLT is, I can't remember, procedural language tab, I think. I can't remember. But basically, this is sort of telling the assembler that this is an external library. So it's not defined in the assembly code. It's a link to the standard C library of the Linux kernel. So here we're calling printf, and we just use that. Now, this program demonstrates basic assembly concepts, including how to load values into register, perform arithmetic operation, how to use loops, make systems calls. And so it's a foundational example to understand lower level programming and perform tasks. Now, I said before, it's good to have the manual pages. So if we look at printf, for example, this isn't the one we want. We want man3. So if we look at the programmer's manual for printf, you can see what it wants is it wants printf, it wants the constant character, the format of how it's going to be, and then any following arguments. So you can use this, it gives you examples, and all of these will be used like the C function, but in assembly you're going to load this information not in a call to the function, but you're going to put this bit in A0, this bit in A1, this bit in A2, etc. And if you remember from the last video, if you go to syscall and you look down at the second table for RISC-V, it does show you this. So this is worth remembering. So these are the system call arguments. So when you make system calls, these are the registers it expects its arguments to be in when you make the call. Right. I hope that this is helpful for you and that it has given you some idea of the basics of the various directives and labels and how to use registers and things. Now, we'll go into more detail about this sort of programming, and we'll look at all of the registers and the register aliases and all of that sort of thing in the next video. And we'll try and see in more detail how we might manipulate the stack, for example, how we save values. So for example, if we have incremented a value, but we want to save it somewhere and then do something else with the registers, we can load that onto the stack and then pull it off when we need it again. So we'll go into that sort of information next, about using the stack to push and pop information and keep the value. So if you like these sort of videos, please like and subscribe, because basically it encourages me to carry on doing it. Yeah, so if you like these sort of videos, please like and subscribe, and I will see you soon. Bye.